Now we're going to look at some common discrete random variables. In particular, we'll look at the Bernoulli distribution, the binomial distribution, and the Poisson distribution. I'm prefacing this by pointing out that even though we're only going to be focusing on those 3 discrete distributions and 3 other continuous distributions in future videos, there are a ton of commonly used distributions. So the goal of this introduction to just a subset of the common ones is for you to learn some basic characteristics, how we calculate key statistics for these distributions, so that you can actually use whatever applicable distribution you come across or that you may need in your future work. Let's start with an example. Suppose that I define a random variable x to be whether or not a biased coin lands on tails. And so in this case, this is a either yes or no situation. So I'm going to let x equaling 1 representing tails and x equals 0 representing heads. In this case, take a minute and see if you can come up with what the support of x is and what the probability mass function for x would be. Okay, so first the support, because we defined it's a binary output, it's either a yes or a no, and we've defined heads as 0 and tails as 1. And then we can give the distribution. So I'm going to give this in several different forms. One of the easiest ways for this particular distribution, because there's only 2 possible values in the support, is just to do a table where I'm going to put either 0 or 1, and then I'm going to do the probability that x is equal to k. So let's just remind ourselves, 0 is heads, and this coin is weighted such that it's 3 times as likely to land on heads as tails. So you could think of, I need some probability of tails plus 3 times that probability, that's heads. So tails plus heads altogether has to be 1, which means the probability of tails is 1/4, right? X here would be 1/4. So probability of tails is 1/4 and probability of heads is 3/4. So I have heads as 0, tails as 1. So that's how I could write this probability mass function in a table. And then we could also imagine visualizing this. If I have 0 and 1 here, I'm just going to put an axis. So 0 would be a height of 3/4. 1 would be, oh, that's definitely a little bit higher. Let's make it look a little more to scale. 1 would be a height of 1/4. And I've drawn this, in theory, I'm trying to make each of these widths just be 1, with the idea that that way I could picture the area of one of these bars as also representing the probability. So the probability of 0 is 3/4, probability of 1 is 1/4, and that corresponds to the areas of those bars. The other way is going to be called a closed form function. What that means is just that I can actually come up with a formula where I can write probability x equals k in terms of something, all in terms of k. Instead of writing it as, here I could write it as piecewise. This is not closed form, this is just piecewise, where I write 3/4 if k is 0, or 1/4 if k is 1. And that's completely fine. But by closed form, I can even try to make this a little bit cleaner by coming up with a single formula that captures this pattern or this relationship. And so you'll notice what's actually happening is I'm going to have 3/4 to some power and 1/4 to some power. And let me explain. I know that when k is 0, I want my output, my probability, to be 3/4. And so basically if I put k right here, 1/4 to the k, that would make this whole term 1. And then I just need to make sure that I have this to some power so that when k is 0, I just get 3/4 out. And when k is 1, I just get a power of 0 because I just want this to go away when k is 1. And so notice that that's going to give me 1 minus k. If I do that, then when I plug in k is 0, I get 3/4, and when I plug in k is 1, I get 1/4. So that's what we mean by a closed form function. It's not always possible to come up with that. There's not always a nice condensed way to do it, but when possible, we'll often do this because it's just more concise than trying to write it as piecewise or as a table. So this is an example of actually a special type of random variable. It's the example of what's called a Bernoulli random variable. Bernoulli random variables are any time you have an experiment with just binary outcomes, success or failure, yes or no, 1 or 0. And here's our notation for random variables in general. The random variable itself is usually a capital letter. And then we have this tilde is letting us just know is distributed as, that's what it's shorthand for. Bernoulli, we just write as shorthand as BER, and then we put the parameter inside. So the parameter is the probability of a success. So for our example on the previous page, we were defining tails as a success. So we had X as a Bernoulli 1/4. That's how we would have written it. In general, if I want to represent the probability mass function of a Bernoulli distribution for any general P, I can do the same idea of what we had, probability X is equal to K, but I'm just going to do it for generic P. So I'm going to have P to the K and then 1 minus P to the 1 minus K. And again, that's for K equals 0 or K equals 1, because that's the support. So let's write that here in my support. Histogram, again, what that histogram looks like will definitely depend on the value of P, but I'll just do one possible one here. So it's possible if this is P, and this is going to be 1 minus P. And then a table, again, similarly to what we saw before, it's just defining this function, but I'll do it generically. So in general, the success is P, and I'm calling that a 1. And then the probability of the other option is 1 minus P. All right, so that's one of the most basic and common random variables. And now we're actually going to build on this idea to get our next random variable. So let's stick with this same example. And let's actually leave it as tails. That way it's consistent as to what we had before. So I'm flipping this coin 4 times in a row, and I want a random variable that describes the number of times the coin lands on tails. So again, put this on pause, see if you can write what the support of y would be, and then give the distribution for y. Okay, so in this case, I could have 0 tails, 1, 2, 3, up to 4. So those are the possible values that y could output or y could take on. And then I want the distribution. So this is really similar to an example we did in our last video, but I'm just going to point out, if I wanted to think, here, let's do it several different ways. I could do a table. I'm going to do that actually on the next page. If I wanted to just find the probability that y was equal to 0, that I have, actually, I'm going to start with one in the middle so you can see something a little bit more subtle. Let's say the probability that y is exactly equal to 2 tails. So again, this is similar to what we did before. You can imagine that I have tails, tails, and then heads, heads. So the probability of tails was 1/4. So I have 1/4 squared, and the probability of heads was 3/4, and then I have that to the 4 minus 2. That is just for this particular sequence, but I could have had tails, heads, or heads, heads, tails, tails. I basically have all the possible combinations where I can choose 2 spots for my tails to go out of 4 open spots. So there's going to be 4 choose 2 ways that I could order these. And that's actually what's going to go in front right here. And so if you notice what's happening in general, if I want the probability that y is k, well, then I'm going to have 4 choose k, and then 1/4 to the k, 3/4 to the 4 minus k. This is a closed form function, so I have just one formula here. And that's one way I can do it. I could also write this as a table. If I actually just calculate the probabilities for all of these 5 possibilities, I can write them in a table, or I can draw a histogram. So typically, when we say give the distribution, if I don't give you which one I want, this is probably the easiest way to do it. But I'll show you on the next page those other 2 options. All right, so here's actually calculating all of those possibilities like we had just talked through. We had just talked through specifically this possibility, but then I was pointing out the other ones. And so option 1 is to do a closed form function like we just did. Option 2 would be as a table. Option 3 is the histogram. And any of these are valid ways of representing the distribution. So this is an example of what's called a binomial random variable. And really, we can think of it as related to Bernoulli because we can think of just repeating n trials of some Bernoulli random variable. In this case, our trials were flipping a biased coin. That was our Bernoulli random variable was 1 flip, and we're going to repeat that n times. And then binomial is capturing out of those n flips, how many successes do you have in those n trials? So a good example, like we said, number of heads or number of tails in n coin flips, number of ones in a randomly generated bit string, number of disk drives that crash in a 1,000 computer cluster. Again, anytime I have independent trials of a success or failure type variable, we can consider the number of successes as a binomial. Here's our notation. So now it has 2 parameters. It has the probability of success, but then it also has the number of independent trials. We need both of those now. And then just as a reminder, our support here is going to be 0, 1, 2, up until n, because you can have n possible successes in n trials. And we can represent it, again, in these 3 ways. So the closed form function is going to look really similar to what we had. It's just I'm now leaving n generic in here as well. We can do a histogram. This was a histogram for that previous example, or a table. This was a table just for that previous example. So usually it becomes much more efficient, especially when you have large n, to use the closed form function. All right, just pointing out that a binomial random variable is really a sum of Bernoulli random variables in the sense that when I'm counting the number of successes, I have defined a success here is when x is equal to 1. And so if I'm saying, okay, the first one was a success, but the second one wasn't, but the third one was, and the fourth one was, counting up the number of ones I get in out of these, or summing these Bernoulli random variables will be summing a bunch of 1s and 0s. At the end of the day, the sum will just be the number of successes. And we will be using this. This is a nice feature that will help us actually simplify calculating some statistics for binomial distributions by using how it's related to Bernoulli. All right, and then we have one last distribution that we're going to derive. To do this, I want us actually to picture that we are trying to come up with the probability of k requests from a given area on some ride-sharing app. Okay, so you're trying to call an Uber or you're trying to call some other type of rideshare. Suppose we know for this given area that on average there are 5 requests per minute. I then would like to come up with what is the probability that I get 2 requests in the next minute? What's the probability I get 5 requests in the next minute? What's the probability I get 10 requests in the next minute? There is a distribution if I think of x as the number of requests that I get in the next time interval. So probability of k requests from this area in the next minute. Again, that's what we're going to define as our number of requests in the next minute is going to be our random variable. We're going to call that x. And we're going to come up with a distribution. So one way we could do this is to think, well, let me break down a minute into 60 seconds. And so in each of those seconds, either somebody requests a ride or somebody doesn't. And so I can think of each second as its own independent Bernoulli trial. It's either a yes or a no. I get a request or I don't. X is now number of requests in the next minute. Well, then that's really just thinking about it as a binomial. I can think of this as a binomial where n is 60. I have 60 possible trials. The probability of a given success, since I had 5 requests per minute, that means I'm going to have 5 divided by 60. That's a probability of a success in a given second. And then I could model it this way. So then I would say, okay, well then my probability would be just this binomial distribution, right? That's the probability that I would get exactly 4 requests or 5 requests or 6 requests, assuming that I either get a request or I don't in a given second. But then you could ask, what if there's 2 requests in the same second? Then this model doesn't work. And I answer, oh, have no fear. We could actually break this up. What if we break up a minute into milliseconds? Okay, so now I have even tinier intervals. And so again, I can say, let X be my number of requests in a minute. And so I'm either getting a request or I don't get a request in each millisecond. And again, I can model this as a binomial distribution. This time n is 60,000 and p is 5 divided by 60,000. I'm just putting it here in terms of lambda and n so you can start to see a pattern. And then the probability that I get, let's say, 10 requests in the next minute would just be plugging in 10 here for k. And then you could play this game again. You could say, wait a minute though, what if there's 2 requests in the same millisecond? And I think you might see where I'm going with this. Because basically we can say, all right, we have the math to handle this. Let's break down a minute into infinitely small buckets. I'm then still modeling the number of requests in a minute as a binomial, but I'm going to take a slight variation on this because I'm letting n go to infinity, right? So I'm modeling it in the sense that yes, it looks like a binomial and some variation of a binomial where I'm breaking this up and letting n go to infinity. So now we're going to take this limit on the next slide, and there's going to be some fun math coming. So here are the key ideas. First, I can expand. So I've got this. Key idea is to remember this is a famous limit from calculus. And so it's going to pop up later in this slide deck. You'll see here, or actually pop up later in this slide itself. The first step I'm doing is actually just expanding the definition of the binomial coefficient and choose k. And then I'm also just expanding this. I'm writing this as this to the n over this to the k. That's equivalent. Then I just do some rearranging, and you'll notice that that definition of my e to the negative lambda shows up right there when I let the limit get distributed through there. So I've now moved it here, and then I still have a limit left, and you'll notice at the end of the day you're going to get some simplification, and eventually when you take this limit at the end of the day, I'm just going to be left with this. And this is the probability that there are exactly k requests in the next minute, assuming that on average we have lambda requests per minute. So this is actually the probability distribution for what we call a Poisson random variable. So let's summarize this. Key assumptions that went into this is we had an experiment that lasts a fixed interval of time. We had x be the number of successes in that fixed interval. This was assuming that each success was independent and that we knew the average number of successes per interval, and that that average number was constant, lambda. So examples that do follow this are random events like earthquakes per year, number of car accidents at a given intersection, number of server hits per second, number of emails per day. Those are all examples that are modeled well with Poisson random variables. Here's the notation we use, and you'll notice here that my support, I can have 0 successes, 1 success, 2. It actually goes up infinitely, but it's countably infinite. because it's just possible integers, but I don't really have a limit in theory. It can take on any integer value. And so I can represent the probability mass function using, because this support is infinite, a table isn't really practical. A histogram is less practical also, although you'll realize like some of the probabilities for very large values often are so tiny you can't even see them. But I'd say most of the time we're using the closed form function, and then you can use the histogram, and then you'll just basically show it for values where you can at least visualize the probabilities. So there are probabilities, for these larger values of 10, 11, 12. They're just so tiny that you can't see them anymore. All right, so let's try an example. Suppose there's an average of 2.79 major earthquakes in the world each year. I want to know, assuming that these earthquakes occur independently, what's the probability of 3 major earthquakes happening next year? Go ahead and put this on pause and try it out. All right, so let's define a random variable. Let's let x be the number of major earthquakes in the next year. In that case, we can think of this as a Poisson random variable, where lambda, again, is the number of successes, or you could think of events, in the given time interval. Since I'm looking at the time interval as being the next year, I'm going to have x be 2.79 per 1 year. And then this is really asking us, what's the probability x is 3? It's actually, this is the exact distribution if you think of this as Poisson. So I'm really trying to figure out exactly the height of this bar here. But we can do it by using the probability mass function of the Poisson distribution. E to the negative lambda times lambda to the k. So this goes 3 over 3 factorial. We'll see that's approximately 22% of chance. All right, so now let's think of this in terms of what I might use, which distribution I might use in a given situation. This is often the hardest part of modeling, is trying to decide what you're modeling and what random variable may be applicable. So based on the 3 discrete random variables we've learned so far in this video, put this on pause and again, try to decide how you might model this. All right, so let's look at the first one. Number of texts I receive in a day. And so again, I'm looking over a time interval. That's telling me I'm going to have Poisson, where lambda would have to be the average number of texts per day. If stock went up or down in a day, now this is interesting because I'm looking over a time interval day, but I'm not counting the number. I'm counting a yes or no, or I'm just looking for a binary. And so in this case, I actually will do a Bernoulli, where P is the probability of the stock going up. That could also be a binomial with n equal 1. So the reason I don't have this as a Poisson is I'm not asking for the number of stocks that go up in a day, assuming they're independent and they're all, they have a constant average. I'm just saying if a particular stock went up. And in that case, the other question where it's binary, where it's just a yes or no, a success or failure, is this one. And so this would also be Bernoulli, which is the equivalent to binomial with n as 1. Number of questions you get correct. So again, I'm looking at a number out of, in this case, n trials. Each trial would be 1 question on a given test. So n is the number of questions. And then p is the probability of guessing 1 question correct. So in this case, let's say that I had, so I'm going to say 1 out of number of options. Let's say I had 5 options on a given question, A, B, C, D, or E, then I'd have a 1/5 chance of guessing it correctly. So P would be 1 out of 5. Number of people who pass through a supermarket checkout. Okay, so again, I have a time interval and I want a number. So that's screaming out Poisson, where lambda would have to be the average number of people who check out in a given hour. Number of people in a random sample with replacement who are CS students. So again, this is a yes, this is a success situation, but I'm repeating it n times because I'm taking a sample. So binomial, where n is the sample size And then P is the probability that any given student is, or the probability of being a CS student. Whether or not a user, oh yeah, we have that one. Okay, so the last one, number of years between now and the end of 2050. This one's a little interesting because it is number of years where I have some type of event. We can think of more than 6 Atlantic hurricanes as like a success or a failure. And so having more than 6 would be a success. Having less than or equal to 6 would be a failure. So in that case, you can think of this as binomial where n is number of years between now and the end of 2050. But then we need to think about what P would be here. P is the probability that in a given year, there's more than 6 Atlantic hurricanes. So I could actually model that by thinking of another random variable. If I assumed, again, that the occurrence of Atlantic hurricanes was independent, had a constant average rate, then Y would be Poisson with parameter lambda, where lambda was the average Atlantic hurricanes per year. So this is a nice one that basically connects 2 of those distributions. And again, the connection comes in figuring out what that probability P is here. So just to put the distributions into context of what we've learned so far, these discrete distributions we focused on in this lesson have really counted number of successes. And what's varied is basically the number of trials or the interval of time over which we're counting the successes. So a Bernoulli was the number of successes in one trial. If I then looked at several trials, that became a binomial. And again, we can see then if n is equal to 1, the binomial turns into the Bernoulli. Contrast this with the Poisson, which was not looking over numbers of trials, but instead an interval of time. Again, I'm still counting number of successes. For the right side of this grid, next week we're going to be learning a continuous distribution called the exponential distribution that will actually be capturing time until success for a given fixed interval of time. And then the other 2, these are actually out of the scope, but I'm going to include them in the appendix if you'd like to learn more about them. This one's called the geometric distribution, and this one is called the negative binomial distribution. And so I'll put that in the appendix, but just note, not in scope in terms of this class, but you're still welcome to dive into those in more detail. Really, a big learning goal of this course is to be able to use new random variables. So there are situations where you're going to see something like this, like a Borel distribution. The goal is that you now have enough understanding about the terms such as support or PMF. We're going to talk about mean and variance in the next couple of videos, where you could then understand the terminology, understand the experiment setup, and be able to move forward from there.